Good morning, everybody. Thank you so much for being able to join us this morning. We have one more talk and then glorious lunch. I know you're all looking forward to it, but hang tight because this promises to be really, really cool. So today we're going to hear from Henry Schreiner building a binary extension. Henry Schreiner is a computational physicist / research software engineer in high-energy physics at Princeton University. He specializes in the interface between high-performance compiled codes and interactive computation in Python, in software distribution, and in interface design. He's previously worked on computational cosmic ray tomography for archaeology and high-performance GPU model fitting. He's currently a member of the IRIS-HEP project, developing tools for the next era of the Large Hadron Collider, LHC. Ladies and gentlemen, Henry Schreiner.
Thank you. So I'm Henry Schreiner, and I'm working with the IRIS-HEP project, which is basically trying to build a set of Python tools to replace and augment the existing C++ that we've been using in high-energy physics since the mid-90s. We actually have a C++ interpreter, if you probably don't want to know that. So we've been building up these tools, and one of the things that was really important with this is we have very high performance requirements in certain areas. We have the largest academic data set in the world, for example. And so with this, it becomes really, really important to be able to do some of the things you'll be seeing today. So I'm going to start with a question. Is Python fast? So of course, this is a completely ambiguous question. A good way to start. But let's just take an example here. This is an article that came out fairly recently, well, within the last 2 years. And they had this problem where they're projecting 1 billion cells. And they had this Fortran code, 1,500 lines of Fortran code that did this in 6 hours and 30 minutes. And finally, they decided to rewrite this in Python. And when they did that, it took 4 minutes. And the reason for this was really they had this high-level language. They had libraries that they could access. It allowed them to easily explore different algorithms. If you have 1 billion cells, you're doing projections. You really want to use something like a KD tree. There's one in SciPy, so they just used that. And so the key behind this is that you have a library. And in that library, you have compiled code that does the hard work for you, and you're still able to stay in Python. So Python has really great performance as long as you can find a library that has your desired algorithm in it, like NumPy or Pandas or something like that. But what do you do if you don't? What do you do if you have some sort of algorithm that's not already coded up somewhere? How do you write that yourself? And that's what we'll be looking at. So first possible solution to this would be you could just dump Python. This is the Twitter and random article on the internet solution. And maybe you're enticed by these other languages. Is anybody enticed by C? But they offer native performance. Well, Python, though, is really easy to learn. It's very quick to write. And it has this massive ecosystem. And I would say each of these 3 things are equally important and incredibly important. So you'll see, and this is where we'll get with the final solution, but you might have already guessed that by the title of the talk, is you can split the driver code. And that's the stuff that usually takes the most time to work on, and that's what you're manipulating and working with. That can still be in Python, and then you can just move the performance-critical code to something else and work together. Before we go on, though, there's a few other possible solutions. One is Numba. This is a just-in-time compiler for Python. This is just as fast or faster than any other solution you can come up with most of the time. But it does have some downsides. You are going to have to do the just-in-time compiling on the device. It's a somewhat heavy dependency, and there's plus sides and downsides. But if you just want to make it faster, this might be the first thing to try. This would be the first thing I would try. Another solution is you can just make Python itself faster. There's a variety of different packages and projects that do this. You have PyPA, of course, for quite a while. Pigeon is a bit newer one. And then there's even forks of CPython to try to make it faster. And CPython itself is actually interested in getting faster now, too. But these sorts of things are in the, say, 5x performance range. Maybe get 5 times faster, at least for CPython. But they don't really make heavy numeric code faster because that's already sits in a compiled language. It doesn't need to be made faster. You may need more algorithms, things like that. And of course, the solution we'll be looking at today is this one. You can precompile. So you can write code using the CPython API, or you can have maybe code sitting in an interface somewhere. And then that can be compiled into an extension, and you can then distribute that. And it turns out that a lot of things you use every day are actually, this is actually done for those things. And this works very, very well. So first, let's go into a little bit of what a binary extension is. If you're using Python now, you probably think in terms of you have some code you're writing, and then you're using libraries. And if you were to write your own library, you'd probably start with this first one, this side on the left here. You'd put all your library code in Python. Well, that code in the library can also be compiled code. It can be a binary extension. And the first one is really easy, but the next one traditionally has been viewed as complex. The examples tended to be rather poor, tended to be things that a really large library like NumPy would do. And there are lots of details in building these and distributing them that, for example, you need to compile on every different platform you support, that sort of thing. But you can achieve really high performance. And one of my goals in this talk will be to show you that this is actually not that hard to do. You can do this yourself. And the tooling around this and all that has become very, very good. And it's really not as complex or as hard as it used to be. OK, so here's an example of of wheels. So I start my example with wheels for showing you something that's not a wheel. That's an SDist. And that thing has a setup.py or a pyproject.toml or some collection of tools that allow a backend to build that. Okay, so that's where your source code sits. Then you have this. This is a pure Python wheel. This is something usually that just contains Python. You'll see the name there. It has the implementation API and platform, and that's just Py3 none any. Okay, and this doesn't have compiled extensions. And then you have wheels that look like this. These are the ones that have binaries in them. And you see you have the implementation, the ABI. Those have actually been the same most of the time in modern Python. And then you have a platform, which is your operating system and your architecture. Okay? And pip will actually do the smart thing. It'll pick the most specific one. So in MyPy's case, they actually have a pure Python wheel, and they compile. So that way, if you're not on one of these systems, it will fall back. But most of you will probably be on one of those systems. There's only a few cases where you end up falling back. So things like NumPy are shipped. There's no pure Python version of NumPy, and they still ship quite well with this. Okay, and we'll be looking at how to make this third one today. So I've already gone over one of the two main reasons to compile. You can get performance. It's also useful for code reuse. There's already great libraries out in these other languages. You can just use those in your compiled extensions. You don't have to rewrite them. Or maybe you want to write something that works in both languages. So this is just a collection of some different libraries that support or that ship binary wheels. Things like PyTorch and MyPy, Pandas, NumPy. And you'll see non-scientific and numeric things in there as well. You see UV, loop, and twisted. WebSockets. OK. So we'll start this talk also with a few disclaimers. This will be a biased talk. I'll be showing you things I work on. But I like those projects enough to join them, and those are the things I know the most about. And we'll also be looking at good practices. Maybe there'll be best practices, but this is definitely not the only way you do things. OK, so you might be now saying to me, well, but it's hard. Compiling code is hard. It requires that you do a lot more than just shipping a Python extension. That's true, but let's divide this problem up into 3 stages. You've already sort of seen them. First, you have the actual writing of whatever you're interested in. So that could be something that's written in C++, or it could be something that is in something, let's say, like MyPy. So you write something that looks like Python, and you still want to compile it. And then once you have something you want to compile, then and notice I'm skipping things like JIT here, because those are not those don't fall into this this area. And then you have a build system. This is something that takes that code and produces the binaries. Traditionally, this has been setuptools and distutils, but this is starting to become a more interesting space and a little less tied to just that one specific view. You'll see that again in a minute. And then you need a tool to do the wheel building, because once you have these things, you need to produce wheels that are redistributable that can go out to all the different platforms. And we'll be focusing primarily on these this path through here. Of course, there's lots of different paths we could take, but this is the one I'll be focusing on today. But I like this because it's a mix and match. You may find some other binding tool or coding tool better for you, but you might still want to build wheels, that sort of thing. Okay, so starting with this bindings and codings, there's sort of two choices here. You can access existing compiled code. So some of the tools sort of focus on that. How do you get C++ or Go or Rust or something out? And there's also from scratch code, which is code you want to write and you want to make it faster. You're not trying to reuse an existing algorithm. And you probably want something that looks like Python. So Python, MyPy, things like that tend to be in this sort of this category. And you might even be able to make your extension optional a bit easier with this one because maybe it's even the same code. So starting with this idea of interfacing an existing library where you're not actually writing the binding, you have this side. That's how you would load a library from C-types, and then you have to build that shared object library somewhere, and you have to do all of the work yourself. And then Python also provides, CPython provides this way to write your own extensions. Okay, and that would be writing this. Now, most of the time, you probably should not be writing this by hand, but I'm just sort of illustrating what you would need, what all these binding tools are actually doing behind the scenes. They're writing stuff that looks like this. And there's only sort of two important things here, and it's this, the fact that you have this name that's dependent on the name of your module, and that's how it knows to look up what it has, and then you list what you have. Okay. Staying on the C interface side, let's just briefly mention a couple options there. C-types is built in. It's very simple, but you're really, it's up to you to get everything right yourself. So it's probably a good idea to try to wrap this in something so that you have some sort of nice interface for your users. And because it's not going to protect you if you do anything wrong. This is a good way to get seg faults in CPython if you make a mistake here. And CFFI is a tool heavily for that I think came out of the PyPA there. They built sort of this tool that reads in the C headers. It's a library you get on PyPA, PyPA. I knew I'd do that. And you can sort of generate some of this automatically and get some extra safety there. All right, going back to the sort of traditional ways to do this, Numba actually also has the ability, besides being a JIT, I remember I said it would not be in this area, but it also has an ahead of time compile, which looks like this, where you can take a little function, you can put a export on the out, and you have to tell it what the module name is. Remember, it has to get that module name in order to produce a extension, because that's part of the interface. And you could compile it. They have this extension for distutils that you can just stick in there. And then you could actually just run this and compile this ahead of time, ship it as a wheel. It would not require Numba. This is very limited, but it's an option. And I've seen it used at least once in a real situation. Another option is MyPy. So this really piggybacks on top of modern Python typing. So for example, you see this on the left, you see a little piece of code. It has type hints. It's valid Python. I can run this with Python. You see Python fib.py, or I can compile it with MyPy, and then I can run it, and it'll be 10 times faster because it's actually compiling. It's compiling the function in the middle. Okay. For comparison, if you did this with the JIT, this would be 35 times faster. You can't do it with the ahead of time compile because recursive is not supported in that ahead of time compile that you saw. Okay. Another popular option is fast, not quite Python, and that's Python. This has been around for a very long time. It's a very good tool for doing this. You can see some code over on the right. This is not probably what you are used to seeing with Python code, but this is actually valid Python and Python code. There is an interface to do that, though there's also sort of this weird hybrid between C and Python that they provide. So it also has a custom language. And that's what you see a bit more often. And there's the code for running it at the bottom. And that's 9 times faster. So it's a little bit slower than the MyPy example for this little piece. And it does have, Python does have some downsides. It can actually bind C and C++, but it wasn't really built for that. It will be very verbose if you try to do that. And it's got a few caveats and drawbacks. But it's really good. It was really designed sort of to allow you to write Python and then make it much faster and compile it. And it works well for that. And then PyBind 11 is a header-only pure C++. interface. And just to unpack that a bit, it means that it's really trivial to add it to a C++ project. There are no special build requirements. It's just C++ 11 or newer. And there's no pre-compile phase. You don't have to Cythonize or use one of these other sort of tools to prepare it. It's just straight C++. You can kind of think of it as if it was a C++ API for Python itself. And it was really designed just to do the binding. It was not designed to really do these other things. So here's a little example of what it looks like to use PyBind 11. You include it. You have your C or C++ code that you're interested in binding. And then you create a module. Remember, it has to get the name of that module somehow. So this is how you're telling it what the name of the module is so it can generate the correct entry point. And then you just take the M is the module object in PyBind 11, and you just can define an add, and it will actually infer the signature and things like that from the thing that you pass in. Okay? And you could actually compile this yourself if you want, and this would just work as is. There's lots of great features of PyBind 11. I list a few of them here. I won't go into them in extensive detail, but it's quite powerful, and it does even supports WebAssembly with PyDide now, and it has a variety of different things that it does. There is one more I want to go into before we sort of dive in a little bit deeper, and there is a sort of sequel to PyBind 11 called Nanobind, written by the same author. And this is C++ 17 only, and it's Python 3.8 only. It's built on top of the fast call API. Very similar API to PyBind 11, intentionally meant to be more limited. And some of these ideas are being backported to PyBind 11 as well. And I have some plots here that show that it is much quicker to compile. It was sort of designed with compilation time in mind because header-only C++ libraries are really slow to compile. The binaries are smaller. Do keep in mind this is for a very basic example, basically like a class and a function. So if your binary size is dominated by your binding tool, then you're probably not compiling very much. But smaller binary size, and the runtime performance is faster. Say if you're looping over something, PyBind 11 is a bit slow because it has a overload dispatch mechanism built in, which is very powerful. And you shouldn't be looping over and calling a function over and over and over in Python. Probably you should try to find some way to wrap the entire thing. But so this is an exciting new project. It's only a couple months old now, I think. All right, so we're going to dive into an example project. I'm going to show you every single line of code you need to create a compile extension for all platforms, everything. So I'll have a reasonable amount of code. The sort of point of this is to show you how much code and maybe point out a few things. I'm not going to walk through every single line. And I'm going to try to do something that's not completely trivial. I'm going to try to take CLI11, which is a command line parser library, my favorite command line parser library. I also wrote it, so might be why. But Microsoft Terminal uses it. So we're going to make a little wrapped version of this from Python. This is not necessarily a good idea, but it's a library I happen to know. It's a good idea to know the library you're trying to wrap so you know how it works, so you know how to expose it. And we're just going to do sort of this minimal bit here. So we want to be able to create an app. We want to add a flag. We want to be able to check and see if that flag exists. And we want to make sure that sort of basic niceties are there. So we want to make sure that we can print the app and something nice will print out, and that we get a key error or something that depends, or it will check as a key error out if we make a mistake. So this is the entire binding code. We're going to import PyBind 11, and it also has some wrappers for the standard library things, and a little bit of setup there. Here we're creating a new exception. That exception is going to come from a key error. It'll make a new rmodule.option.not-found for us. And then that will automatically wrap the exception, so we don't need to bother with it down here. We could throw a py : key error if we wanted to. But this is more declarative, which is nice. And then we create our app, and then in the app we're going to define a few methods. And so we're defining each one. Notice we even have some dunder methods there. We define getItem and stir. And then the thing on the other side can just be a Lambda function. Sometimes it's like there in the middle, you see that overload cast. There it's actually it's binding to the function itself, and it's overloaded, so you have to pick which one. Or you can just use a lambda function in C++, just throw that in there, and let the compiler figure out which overloaded one you're after. Or you can do more work if you want. So it's really quite nice to be able to just use the lambda functions there. And that's the binding code. Okay. I said I'd show you every line of code, so there's the init.py. And also tests. You should always test anything, so let's at least write some tests. So this is basically the same thing I just showed you, but in test form. Okay? All right, we're going to leave that for a minute. When we go back to the yellow slides, we'll be back in our example. Let's talk about build systems. So there are some great examples of pure Python build systems that are now using PEP 621. Things like Flit and Hatch and others, including actually setuptools now. But building binaries, your choices are somewhat limited. So setuptools and distributools has a lot of drawbacks. It is capable of building a file from C or C++, but it really wasn't extended and doesn't add a lot of things, just sort of basic things that most build systems would have, like multi-threaded builds or partial rebuilds and features of your compiler, and just all these things that are built into tools like CMake and Meson and stuff. You can't even tell it what C++ standard you want to target. It does actually have native Python support, though. setuptools does. So this then has been extended by a lot of different packages. So MyPy extends this. NumPy distributils. There's lots of examples of things that then write sort of extensions and work with this, even though you're kind of delving into the internals quite a bit. And then there are a few from scratch. I don't think actually inscons, I'm not sure if that fully counts because that's also using at least a little bit of distributils. I saw distributils showing up inside its code base. But I do want to point it out just because it was one of the earliest adopters of PEP 517 that supported compiled builds. But Meson.py is out now, and Motrin is one for Rust. So we're starting to see some of those. There's also Scikit-build, which is sort of what we'll focus on today. Right now, unfortunately, it just wraps setuptools, but there is a planned move, and I'll talk a little bit about the plans to try to get it over into this onto that side of the screen. PyBind 11 actually has this nice little extension as well for setuptools. So you can just grab this setup helpers, and then you can do a PyBind 11 extension. You can tell it what C++ standard you want, and just go with that. If you have something that's simple, you can do that. So Scikit-build is a tool from the makers of CMake to allow you to use CMake from Python. And this started back in 2014. It was announced at SciPy. It was renamed. It was originally PyCMake, and then it was renamed a bit later. And two of our most popular packages are the CMake package for Python. So if you do pip install CMake, you get CMake for pretty much all the binary, in all these different areas. And it has some really nice tooling. I helped sort of update some of that. And you can do the same thing with Ninja. You can pip install Ninja as well. And that comes from the Scikit-build project. And this is really exciting because it would allow you to use a very powerful existing build system, the most popular C++, C, CUDA, et cetera, build system directly from Python. It has a couple new maintainers that joined in the last 6 months or so. And it's definitely an exciting example there. And just also, if you need a refresher on CMake, I wrote a book on CMake, so you can go check that out. Years before this. Okay, as long as you use modern CMake, it's actually quite nice, and you'll see that. So there are some plans. The idea is that we'll try to develop a Scikit-build core that will be a PEP 517 builder, avoiding setuptools and distributils. That will give us, hopefully we can sort of give a compatibility layer so the existing users will still work. We'll also have a way to do a direct build. And then hopefully a proper setuptools extension, because currently that's still sort of how you put these things together. But there might actually be some generalization that's happening in the, we're going to talk about this a bit in the packaging summit later. So it might be nice if we could sort of generalize and not write an extension for every single system out there like Hatch, Poetry, et And then also we need a extension discovery mechanism. We might be working with CMake itself to do this, because it would be really nice if we could just stick this in our Python requires, say, hey, I want PyBind 11, and then just immediately find it. Right now you have to do a little bit more work to do that, and you'll see in the next page that I just avoid this entirely in the example we'll be showing. Okay, and you can read more about that proposal there. All right, so going back to our project, this is our CMake list. This is the whole thing. We're actually just grabbing both PyBind 11 and CLI 11 from GitHub, because that way we don't have to deal with the fact that we don't have a nice way to grab where PyBind 11 is. And we have to do this with CLI 11 anyway, because it's not a Python package. Okay. So we're just grabbing those. Then we add a module. This is added by PyBind 11. We link them. We tell it we need C++14 because we used one C++14 feature. And then there's an install. And that's the CMake list. Right now, you have to write this setup.py as well. And this is what I mentioned about the wrapper for the regular setup. And we have to stick this in. Some of this does actually have to be inside the setup.py and can't be pulled out to setup.config. Not all of it, but some of it does. Okay, so those are really almost the entire build system. The only remaining thing is we need to also request Scikit-build, and our build system requires. Okay, and we'll actually fill out some more of the pyproject.toml. We're not done with that yet, but we'll leave it there for now. The next thing we need to do is to redistribute. So we need to build wheels. So you could distribute on Conda Forge. I'm not going to go into that in detail just because it's really mostly automated. You just have to go out and write a recipe, and their CI will build that for you. And a lot of the stuff that we do, we really want to make sure we distribute on both. We'll be focusing on PyPA. And in there, we have a variety of different things that we have to deal with. So on Linux, we need to build inside of a controlled Docker image to make sure that we're not using something that's not allowed in the mini Linux specification. We don't want to pull something in that, or use a version of glibc that's too new or something like that. So there's mini Linux and Musa Linux images, and there's also multiple architectures for all of these. And you really should be running audit wheel afterwards to make sure that this is packaged up into a nice mini Linux image, or mini Linux wheel. macOS, you now have to worry about the target version. You have to pick what version you target. It's a really nice feature of Mac, but you also have to think about it. And you also need to make sure your Python was compiled with whatever that target was. So you really want to use the python.org Python. You don't want to grab the CI or whatever, because that was probably targeting the thing it built on, which is probably macOS 10.15 or something like that. But you really want to use the 10.9, one that targets 10.9 from python.org, so that you have your choice of what you want to target. Okay. And then you have to worry about cross-compiling for universal. And there's a separate tool there. Same thing again for Windows. Windows is actually the easiest of these, because you can pretty much grab Python from anywhere and it'll work. Please make sure you still distribute 32-bit, because you still see some 32-bit Pythons floating around, and even a laptop, I have one. And then there's beginning to be ARM support on Windows as well. And then there's beginning to be there's a very fairly young tool called the Wheel that's appearing here that also helps you sort of package and make sure anything that you use is bundled into your wheel for you. So I want to go straight into CI-build-wheel. This is a tool to do all of this for you. It supports all the major CI providers, and it runs locally. It ran locally for Linux for a long time, but it actually supports Windows and macOS locally now too. And this tool has really taken off in the last couple of years. I joined it, I think, in 2020, and then made a push to get this into the PyPA. It joined. And we have I think we have at least 600 users now, which include almost everything you saw on that first slide, like MyPy and NumPy has just moved to it. And so this supports sort of all the different possible wheels that you're likely to want. So you can target any version of macOS. You can do Apple Silicon for all the Python versions that support it, which is 3.8 and newer. All the variants of mini Linux, including the ones that you might have to emulate, or some CI providers have native runners. Musa Linux was added fairly recently. PyPA supported. And this will also go through, do the repair step I showed you. It will test your wheels. If you tell it what command you need to test it, and it'll install it in a brand new environment and make sure that your wheel actually does what it says it does and passes your tests pulled directly from the wheel you built. Okay, and the defaults are all pinned. You can't unpin those, but they're all pinned and updated regularly. Okay, and then there's some new features that have come out recently. Right after we joined the PyPA, we had cibuildwheel 2. That included our pyproject.toml support, which you'll be seeing in a minute, which I'm quite happy about. And then we've been, over the last few months, we've been adding even more things like the overrides, which is powerful, but I won't be showing you today. And as I mentioned, the local runs, experimental Windows ARM support, even though we don't have any runners for that yet, in CI, that is. And in 2.5, which was released this morning, we also have support for the stable ABI. So you can do a limited API stable ABI build, and it will build the first wheel and then just test all the rest and not try to build it again because it's already built. And you can also build directly from an SDist. You can just grab an SDist off PyPA and then run cibuildwheel on it, and you can produce your wheels. And we are supporting toml now. A few tips. This is how you'd run it locally. When you do it locally, you just have to, and I'm just using pipx run there, but any way you like to run it, I would recommend that way. You just tell it what platform you want to target. That uses Docker for Linux, so that works on your Mac or Windows or whatever, wherever you are, as long as you can run Docker. You can target Linux, but you always have to tell it the platform, and that way it knows that you intentionally are trying to build wheels because it may take a while. And then this is a really good tip for keeping it up to date. We do provide an action, and this will keep your action up to date. All right, so going back to our pyproject.toml, I can now finish showing it to you. Here we tell cibuildwheel what command to run for testing. That will turn on the testing feature. And then we also tell it that I need to install with the bracket test when I install the wheel, because that's where I put the dependencies. And then this is how you would do this for adding Apple Silicon. You have to pick for Apple Silicon if you want to use universal wheels, which have both architectures put into one place, or if you just want a native wheel. And so you just opt in for whichever way you want. Okay, and that's really the configuration. There's a lot more options here. You can customize that however you like. And you can do it through, everything can be done through environment variables, but this is a lot cleaner and nicer. And lets you run it locally without having to redo all your environment variables. Okay, and there's the PyTest stuff. Okay, so now I'm going to show you the workflows. This is the longest piece, but I think you'll see it's not too bad. First thing here, and I'm doing this in GitHub. You could do it some other system if you wanted. First, we're going to do this whenever we click publish, or do publish from the GitHub command line, whatever way you like to do that, or if you want to manually trigger it. And then, because this will probably take a while, you're going to be building a lot of wheels. Then we're going to build an SDist. So that's you can just use build for that. So PyPA build is a tool that can build wheels and SDists, and you can just use that to build the SDist. And pipx is built into GitHub Actions, which is really nice, and Azure. So you can just do that one line. You don't even have to get a version of Python. You can just use pipx. It's a supported platform, which is fantastic. It's actually used internally inside cibuildwheel's action. The action's only about a page long. Okay. All right. And we just added something to Nox that does that too. Okay, and then you now want to build your wheels. This, I assume that you would think this one would be the most complex one, and it might technically be, but it's not too bad. We mostly just do PyPA cibuildwheel, and then it's a good idea to use an exact version there, and then use Dependabot to do that update for you. So every time we release it, it'll then ask you to update, and that way your wheels don't crash because maybe we changed something. And that's about it. We're running on all the platforms. Okay, and then finally, assuming you want to upload this to PyPI, you could also just download it from the interface and manually upload it yourself. But you can, because it's an artifact. But here's how you would upload it. And you want to make sure your wheels and your SDists are finished before you do that. And we're done. This is what comes out. This is what that produces. This is every wheel, and we put a minimum version of 3.7. So this is every wheel. It supports 3.6 and newer. And that's it. You can see the Mac OS wheels there. There's the universal. There's the one for the Intel architecture. There's Mini Linux, Musa Linux, the two different Windows ones, the PyPA for 3.7, 3.8, and 3.9 are over there. They're all there. If you're in the back, biggest point is there's a lot of things here. And you saw how much work had to go into that. Not that much. And this scales. This is something you can do on a very small little project. If you look at the CI-build-wheel examples page, you'll see small little projects, you'll see medium-sized projects, and you'll see giant ones. So this scales really, really well. It's simple enough for small projects and powerful enough for complex ones. Also, maybe now that I've given you this sort of intro into what's possible, maybe you could think outside the box and mix and match these things in unusual ways. So here's an example of Clang format wheel. And so that uses Scikit-build, which actually triggers LLVM's build. It uses CI-build-wheel to then build Python independent binary wheels. You only need one, so it just picks like 3.8 or something. And then it makes sure that the final names don't have the 3.8 part, because it doesn't depend on CPython, but it does depend on your platform. And then these are like 1 or 2 megabyte binaries that sit on PyPA. There's no binding here. This is only an entry point. But this means you can just do pipx run Clang format, and you can get Clang format in a second or two on pretty much any system that you can run on. There's even a pre-commit wheel. You can run this on pre-commit CI yourself. Before this project came out, I've been fighting Conda Forge to try to get this thing under, I think it was 500 megabytes to fit into the, to try to get a Conda environment that would fit in under 500 megabytes with Clang format in it so that I could run it in pre-commit.ci, because there was a limit. Maybe it's 250, I don't know. And this was 1 to 2 megabytes per wheel. So this is a really fantastic use, I think, of some of these things we've been seeing. If you want to just quickly jump in and start working on this, I just want to do a little plug for something that I work on. One of the Scikit-hep pages, products from Scikit-hep, is this developer pages. I'm going to try to do a lightning talk on this too, because I really like it. And you can quickly make a package using even their cookie cutter. So you could just say pipx run cookie cutter, give it there. PyBind 11 and as of yesterday now Scikit-build are backend choices. PyBind 11's been there for, pure PyBind 11 setup tools has been there forever, but Scikit-build just was added yesterday. So we now have 11 different backends, a lot of pure Python backends, Hatch, Poetry, whatever you'd like. Setup tools, 2 different setup tools, one for PEP 621. But, and then for compiled ones, we also have Motrin for Rust. So if you wanted to start a Rust package, this can get you started too. And all this is tested with Nox and GitHub Actions. And we even have this also very new repo review page. So you can just type in the name of a repository, and you can type in a branch name, click the button, and then Pyodide will run Python 3.10 in your browser, and it will then spit out what guidelines you're following and what you're not from the developer guidelines. So that's quite fantastic. I would highly recommend taking a look at the scikit-hep.org developer page. So key takeaways here. The code you just saw is, I just put that into a repository if you want to look at it, and you can just see exactly, you can see it work because it's there in the GitHub Actions. Logs and things are there. And then if you want to sort of find out a little bit more about this, my blog is at isinumpy.dev. That includes links to the most important things, I think, that are here as well. There's a link to the Scikit-hep developer pages, and there's links to the PyBind 11 examples and to the Scikit-build examples. And PyBind 11 has some very nice examples, including just using setup tools, using Scikit-build, or wrapping CMake yourself using setup tools. And then finally, to end with a little bit about me, these are some of the things that I work on. These are the projects that I'm involved with and a member in some form or some form or way. If you go to, but most importantly, again, my blog link, which is actually old there, that will take you there too. But isinumpy.dev or isinumpy.gitlab.io will take you to my blog. Okay, and I guess we don't really have any questions, so thanks for your time.
Thank you again. We do not have any Q&A at this year's PyCon, so if you do have any questions for the speaker, I encourage you to ask them over here outside of this room. I also just want to take a moment before you leave for lunch to give a nice shout out to our audio team and to our transcriptionist for kicking butt today.